when X-rays scatter off near free electrons? Why does the outgoing light shift toward red? And why does the red shift grow as the scattering angle gets larger? In the energy filament theory, Compton scattering is one closure and settlement events. A coherent wave packet meets an electron that can accept a transaction. The interaction closes as a single discrete deal, and a bigger geometric turn costs more momentum and energy. So the packet leaves with a slower cadence. Classical wave pictures struggled here because they wanted energy to smear continuously across a wavefront. Yet experiments act like each encounter takes a bit. The mainstream fix is the photon as particle collision story, which predicts the numbers well, but many people still don't. Had an intuitive movie in their head for how something wave-like could behave like a one-time trade. This picture gives you that movie without giving up wave propagation. The wave packet is wave-like while it travels, because it relays through the energy sea as a bounded, organized packet. But when it reaches a structure with an available closure threshold, the exchange is not a smear, it is an accounting closure. One packet, one electron, one settlement. Now for the angle, imagine you're pushing a shopping cart fast down a hallway and you bump into someone. If you only graze them, your direction barely changes, and you give up only a little of your forward shove. If you are forced into a big turn, or close to a U-turn, you must dump much more of that shoving into the interaction to accomplish the geometry. That dumped shove is momentum and energy transferred to the electrons. And because the packet is a finite single unit in a thresholded deal, the cost is deducted from that unit, not spread into a continuous fog. What remains has less forward drive and a slower rhythm signature, so its frequency drops and it looks redder. The bigger the deflection angle, the bigger the required turning cost, and the redder the outgoing packet. If you prefer the formal mainstream ledger for momentum conservation, keep it. This is simply the same ledger translated into an everyday sentence. Changing direction has a price, and the price comes out of the packet's budget. This also explains why the event looks discrete on a detector. In a thresholded closure, you don't paint a continuous street. You record a series of separate settlements, individual electrons kicked out, individual packets redirected, each with its own post-deal cadence. Again, wave behavior belongs to propagation, while discreteness belongs to closure. And there's a useful extension hiding in the same mechanism. Not every disturbance in the energy sea becomes light that can travel far. Many wolf-bee signals die at the source because they never clump into a stable packet, or they miss the right window, or they don't match a channel that can carry coherence. They pop like tiny near-field bubbles and get swallowed back into the local environment. The universe isn't glowing everywhere all the time. Most attempted emissions never make it out of the door. The punchline is sharp. Compton redshift is not mysterious fatigue. It's the geometric cost of a turn paid in one discrete settlement. Bigger angle, bigger payment. Next up, we'll push the near-field story further with frustrated total internal reflection. How light can cross what looks like a forbidden gap, not as a ghost wave, but as a near-field grab handle that can still close a deal. Tap follow, share it on New Physics, Clear Universe.